Understanding the thermodynamic relationship between polymorphs is critical in pharmaceutical formulations, where stability and solubility can significantly impact drug efficacy. As we discussed previously, polymorphs are different crystal forms of the same compound, and their properties may differ. The relationship between two polymorphs can be classified as either monotropic or enantiotropic. We previously discussed how to determine this relationship using differential scanning calorimetry, but let's talk about them in more detail. In a monotropic system, one polymorph remains stable across the entire relevant temperature range. If you begin with the stable form, it is impossible to obtain the metastable form through thermal activation. This characteristic is key to controlling the quality of a drug and its formulation. Let's go over an example. Form A is the metastable polymorph, and Form B is the stable polymorph. By heating Form A above the transition temperature, we can obtain Form B, but starting with Form B won't allow us to reach Form A. This irreversibility defines a monotropic relationship. If we were to examine a DSC of the conversion of Form A into Form B, we would see that Form A would have a lower melting point, followed by an exothermic transition to Form B, and then Form B's melt. Form B would have a higher melting point and a higher heat of fusion, because it is the more thermodynamically stable form. In an enantiotropic relationship, there exists a transition temperature, where the identity of the more stable polymorph can change depending on if you are above or below it. This means that both polymorphs can coexist depending on the temperature. The lower melting form will be thermodynamically stable below the transition temperature, and the higher melting form is stable above the transition temperature. Flunemic acid is a great example for this. Form 3 is stable form below 42°C, and Form 1 is the stable form above 42°C. At room temperature, Form 1 crystals show a slow transformation to Form 3, and Form 3 crystals transform to Form 1 around 115°C. The reversible solid-state transformation between these two forms is an important characteristic for enantiotropic relationships. To differentiate between monotropic and enantiotropic polymorphs, we employ some key rules based on thermal analysis. The heat of fusion rule states that if the higher temperature melting polymorph has a lower heat of fusion, the two polymorphs are generally enantiotropic. If the higher melting polymorph has a higher heat of fusion, then this form is generally the most stable and monotropically related to the other polymorph. The heat of transition also provides insights. In monotropic systems, the transition from the metastable form to the stable form is exothermic. However, in enantiotropic systems, the transition from stable form to metastable form is endothermic above the transition temperature. This demonstrates the reversible nature of transitions in enantiotropic systems compared to the irreversible transition in monotropic systems. Understanding these thermodynamic characteristics is essential. In cases where the active pharmaceutical ingredient, or API, has multiple polymorphs, an energy transition phase diagram must be utilized, as the monotropic and enantiotropic relationships differ for each pair of polymorphs. In summary, understanding whether a relationship between two polymorphs is monotropic or enantiotropic is essential for drug formulation. This knowledge helps to determine the stable temperature range for the desired polymorph, guiding the design of processing conditions to ensure stability throughout the production of the active pharmaceutical ingredient.